Machine Learning for Absolute Beginners. Chapter 3. Machine Learning Categories. Machine learning is a vast field, incorporating hundreds of statistical algorithms. Selecting the right algorithm is a continuous challenge. Before diving into specific algorithms, it's crucial to understand the three main categories of machine learning and how they handle input and output variables. Supervised learning. Supervised learning mimics our ability to learn patterns from known examples to achieve repeatable outcomes. An example of this is Toyota's approach to designing its first car prototype. Instead of starting from scratch, Toyota engineers deconstructed a Chevrolet to understand its design. They analyzed the input, or components, to comprehend the output, which is the finished car. In machine learning, this process is replicated by analyzing the relationship between input and output data to uncover underlying patterns. Here, input data is termed as the independent variable, denoted as uppercase X, while output data is the dependent variable, represented as lowercase y. For instance, in face recognition, the dependent variable might be the coordinates of a rectangle around a person's face in an image. The independent variables could be pixel colors and positions. The model uses numerous examples to learn and generate an algorithmic equation, which can then predict outcomes based on input data. However, building a supervised learning model requires a labeled dataset, where each example has known input and output values. Common supervised learning algorithms include regression analysis, decision trees, k-nearest neighbors, neural networks, and support vector machines. Unsupervised learning. In unsupervised learning, the output variables are unlabeled, and the relationships between inputs and outputs aren't known. Instead, the focus is on analyzing input relationships to discover hidden patterns. For example, when analyzing purchasing behavior, distinct clusters of small and medium-sized enterprises, SMEs, and large enterprises may emerge due to differing procurement needs. Unsupervised learning helps identify these patterns, allowing further analysis. It is particularly useful in areas like fraud detection, where unclassified attack patterns are detected without prior labels. Companies like DataVisor leverage unsupervised learning to identify fraudulent online activities. Traditional solutions rely on labeled data, whereas DataVisor detects new attack patterns without predefined labels, identifying suspicious connections between users. While unsupervised learning uncovers hidden patterns, its predictions can be subjective due to the lack of labeled outputs. Algorithms used in unsupervised learning include k-means clustering, social network analysis, and dimensionality reduction. Semi-supervised learning. Semi-supervised learning is a hybrid approach that combines supervised and unsupervised learning. It utilizes both labeled and unlabeled data to improve prediction reliability. By building an initial model with labeled data, this technique then uses the model to label the remaining unlabeled data. The model is retrained iteratively, integrating newly labeled data. However, there is no guarantee that a semi-supervised model will outperform one based solely on labeled data. Reinforcement learning. Reinforcement learning, the third category, is the most advanced form. It builds its prediction model through feedback from trial and error, learning from previous iterations to achieve specific goals. Reinforcement learning is akin to playing a video game, where the player learns from experiences to improve performance. Similarly, algorithms train models through continuous learning, with measurable performance criteria. A prominent example is self-driving vehicles, where avoiding crashes earns positive scores. One specific reinforcement learning algorithm is Q-learning. Here, the environment consists of states, S, such as obstacles in a video game. Possible actions, A, are the responses to these states. The value Q starts at 0 and adjusts based on positive or negative outcomes. Q-learning involves exploring different actions in various states to maximize Q. Although the concept sounds simple, implementing it is computationally demanding.